we're going to be learning how to calculate the percent composition both for the elements in a compound and for the water in a hydrate. So it's pretty simple. When we do it by mass, so the percent mass or the percent composition, it's the percent of each element in the compound. That should be pretty easy to do. And when we're talking about percent water or percent comp of a hydrate, it's the percent water in the hydrate specifically. So just to go over this, a hydrate is a compound that has water trapped to it. They are often colored because they often have transition metals that, when in water, create colored compounds, which is where we get, or where we used to get, most of our paints from. Okay, so the water in a hydrate can be removed very easily. All you have to do is typically heat them up, and you remove the water just like if you use heat in your dryer. That's the whole idea. It tumbles it, and the heat evaporates the water quicker, and the water dries out. So same idea. The formula is right here. It is percent comp is the mass of the part over the mass of the entire thing times 100. In the case of the element, the part is the element, and the whole is the GFM. And in the case of the hydrate, the part is the mass of the water specifically, and then the whole is still the GFM, including the hydrate. So once you see it done once, it should be pretty easy. So we're going to start with the easy one. So we are going to be doing percent comp of C3H8, better known as propane. It's pretty simple. So to save time, the GFM for this guy is So the GFM is 44 grams per mole. So the way I do this is I write it out like this. My percent carbon is going to be the mass of the carbon in the equation. There's 3 of them. Carbon weighs 12, so 12 times 3 is 36. So it's going to be my part over my whole times 100. So my part in this case is going to be 36. It's the mass of the carbon. And my whole is going to be 44 because that's my GFM of the entire thing. So now I multiply them together, or divide them, and divide and multiply by 100, basically do your math, and you get 81.8% carbon. Now, since there is only 2 elements in this entire formula, I could just go 100 minus 81.8 and I'll get my percent for hydrogen because it's got to add up to 100. If I want to double check it to make sure I'm doing it right, and if I'm asking to see the work, which I am in this case, you do it separately, and it's going to be, since there are 8 hydrogen and hydrogen weigh 1, it's going to be 8 over 44 times 100, and that adds up to 18.2% H. And that's how you do it. They are very, very simple calculations to do. Just be aware, if they don't add up to exactly 100, if they add up to like 99 point something or 101 point something or 100 point something, that's totally fine. That just means you rounded down on, if you rounded down in both cases, then you might be slightly under 100, or if you rounded up in both cases, you might be slightly over 100. But as long as it's within like 1% of 100, you did it right. If it's wildly off, then you have a mistake. So now we're going to do the next one, C6H12O6. The GFM for this guy is 180 grams per mole. So there's my GFM, and let's do it. So we've got my percent carbon, my percent hydrogen, and my percent oxygen. So I'm not going to write the whole formula out. I don't have the space, so I'm just going to do the numbers. So 6 carbon is going to be 72 over 180 times 100. 12 hydrogen are going to be 12 over 180 times 100, and the 6 oxygen are going to be 96 over 180 times 100. These should be pretty simple to do. So you do your math and you get 40% carbon, 6.7% hydrogen and 53.3% oxygen. Add them all up, they add to 100. You did it right. Done. Okay, for the next one, I do want to mention they like these problems because here's the issue. You look at this, first off, we'll get our GFM. So our GFM is 68 grams per mole, right? But how many nitrogen are in this equation? So when you do your percent N versus your percent H, what you have to worry about is the fact that there are 4 nitrogen in this equation. There's 3 because of the parentheses, right? But then there's also 1 more on the outside. And when we do our percent comp, that counts. It's all in the same equation. So we have to worry about the mass of 4 nitrogen, not 3, which is 56 over 68 times 100. And then if we did the next one, it would be, for the hydrogen, it would be 12 over 68 times 100. And the reason there's 12 is because this 3 multiplies the 4 in the hydrogen by 3 and making 12. So we end up with 82.4% N and 17.6% H. So be careful there. We're going to do one more, and then we're done with our elements, and we'll go on to the percent comps of a hydrate. They look more complicated. They're actually not. So for this one, our GFM, I don't have it with me, so we're going to have to add this up. So let's figure it out real quick. How many, let's see, we have 1N, which is 14. We have 7 H's, which is 7. We have 2 carbons, which is 24. And then we have 2 oxygens, which is 32. Add all that up. And our GFM is 77 grams per mole. So now we're going to do our percent N is going to be 14 over 77 times 100. Our percent H is going to be 7 over 77 times 100. Our percent carbon is going to be 24 over 77 times 100, and our percent oxygen is going to be 32 over 77 times 100. So let's see. This is 18.8, 9.1, 31.2% carbon, 41.6% oxygen, and if we added those up, 18.8 plus 9.1 plus 31.2 plus 41.6, we get 100.7, which is fine because I guess I rounded up more than I rounded down, so we got a little bit higher than we needed to. That's totally okay. So that's how you do percent comp for the elements. So it is a lot of work, even though it looks like 4 problems. It's really way more than that. Now, percent water is simple, all right? All you need to know is how much do the waters weigh, and then how much does the whole thing weigh. So this is, I've mentioned this before when we were doing the mole formula. For this, we know that water weighs 18. There's 2 H's, they weigh 1 each. There's 1 O, it weighs 16. 2 plus 16 is 18. So 5 waters here is going to weigh 90. And in this case, 3 waters will weigh 54, I think. 54. And now we're at 2 waters, which are going to weigh 36, and now we're at 0 waters, which are going to weigh 0. We don't even have to do the math on that one. Okay, and then my CuSO4, we could do it separately if we wanted to. I'll do it off to the side. It's 1 Cu, which weighs 64, 1 S, which weighs 32, and 4 O's, which weighs 64. Add the whole thing together, and you get 160. So this guy weighs 160 each time. So when I get my total GFM, 160 and 90, for this problem it's going to weigh 250. For this one, 214. For this one, 196. And for this one, it's just 160 again. So when I do my percent water, it looks like this. Percent water equals the part, which is the water, so 90 over the whole, which is 250, times 100, so that's going to equal 36% water. Okay, next one. $54 over 214 times 100, which is going to equal 25.2% water. The next one is going to be 36 over 196 times 100, which is going to be 18.4% water. And then the last one is going to be 0% water. So that's how you do percent water. I did it for the same CuSO4 molecule every time, but every hydrate is different. So while the water part's going to be done the same way, and you're going to add the two together just like always, if you use a different first part of the molecule, because there are lots of them, you'll have to do that as well. That has to be done each time if the formula changes. Also, notice I didn't mention this, but I am going to mention it now. When we do a lab where we actually take this hydrate and we scoop it out, and it's a nice dark blue color. And then what we do is we put it on a hot plate and we heat it up. And as the hot plate heats up and you see some steam, which is water vapor coming off the hydrate starts to change color. So when it's fully hydrated, it's blue. And then eventually it's going to become less hydrated and become light blue. And then eventually it'll start becoming a blue-gray. And then when all the water is gone, it's going to be 100% gray. And that is how you remove the water from a hydrate. You just heat it off. The nice thing about this is we can weigh it here. We can weigh it when it's like fully blue. We can weigh it at the very end, and we can compare the weights, and we would expect to see a 36% decrease in weight because 36% of it was water, and if we truly removed all the water, then it should weigh 36% less when we're done. It's not necessarily going to be 160. I could scoop out, 10 grams of material, and then if I heat it and remove all the water, it's going to be 36% lighter, which would be 3.6 grams. So the amounts don't matter. It's the percentages that are important. And the nice thing is at the end, we can add the water back in, and what do you think you'll see? It should be pretty obvious. If you put the water back in, it's going to go right back to blue. Now, granted, in real life, the blue's never as good the second time around because when we heat it, we actually break some of the chemical bonds here, so we don't get a perfect hydrate back every time, but it is good enough for what we need to do, and that's everything you need to know about percent comp of both an element and a hydrate.